Assalamualaikum and a good day to my panels. My name is Syahmah Shafie. For the bachelor degree project, my study is about thermal and mechanical properties of biotray from coconut fiber and starch composite. My supervisor is T.S. Muhammad Syafiq bin Jumali and co-supervisor by Dr. RIDHWAN bin Jumaidin. This is my presentation outline. There are 5 chapters will be presented. Chapter 1, Introduction. Background of study. Recently, more environmental friendly products need to develop are increasing due to the compilation of landfill of non-biodegradable waste. The so-called green biomass are constantly developed by incorporating biofiber into renewable resources based of biopolymer. This research aims to develop thermal and mechanical properties of biotray by using thermoplastic cassava starch and beeswax reinforced with coconut fiber. Problem statement of my study. 1. Environmental problem caused by non-biodegradable products. 2. Abundant waste of natural fiber. 3. Poor properties of thermoplastic starch. And 4. The depletion of petroleum resources. My objective of study are 1. To develop biotray from coconut fiber by using thermoplastic cassava starch and beeswax. 2. To determine the thermal properties of thermoplastic cassava starch and beeswax reinforced with coconut fiber. And 3. To investigate the mechanical properties of thermoplastic cassava starch and beeswax reinforced with coconut fiber. Scope. 1. Coconut fiber and cassava starch as the fundamental of material modified with glycerol and beeswax. The composite was developed by using dry mixing and hot pressing. Thermal properties has been determined by using thermographic analysis (TGA), while mechanical properties has been investigated by carrying out tensile and flexural testing. Mold was produced to make the product sample. Chapter 2, Literature Review. Thermoplastic starch. TPS is a material obtained by disturbance as modified to the structure of starch granule when handled in the presence of plasticizer that do not easily evaporate during processing with low water content and thermal and mechanical forces. Coconut fiber. Coconut fiber is highly lightning resistant and extremely durable. So, it has ability to absorb or release humidity. Glycerol. Glycerol is naturally occurring chemical. It is used for the processing of biodegradable starch as a plasticizer. Plasticizer offer greater stability in the structure of polymer, reduce intermolecular forces and temperature of the glass transition. Beeswax is a natural hydrophobic and biodegradable wax produced by the honeybees. The coating with the beeswax is an interesting technique for reducing water vapor permeability of hygroscopic biodegradable material. This is some of my review paper in my literature review. During my study, there is no paper about my study. So, I have supported some of review paper in my final report. Chapter 3, Methodology. This is my methodology flowchart. Start with the material. I'm using glycerol, cassava starch, beeswax and coconut fiber. Then by using dry mixing hand hot pressing process, and then I produce a sample and then reinforce with the coconut fiber, also with dry mixing and hot pressing. Then go to the analysis, which is thermal and mechanical analysis. The material that has been used in my study, they have 4 main: coconut fiber, cassava starch, glycerol and beeswax. Okay, this is extraction of coconut fiber. Start with the extraction of the coconut and then go to the water retting process about 2 to 3 weeks after is already. This is a flow of extraction of coconut fiber. Start with the extraction of coconut. Go to the water retting process about 2 to 3 weeks. And then retrieving fiber from the remain of water retting process. Dry sun of the fiber. And we got the fiber, coconut fiber. Okay, this is fabrication of cassava starch and beeswax. Start with the produce TPS, and then we added beeswax, blend the mixture to get the homogeneous blend, compact to the mold, put mold in hot pressing machine for 1 hour, and we got the sample. Okay, this is fabrication of cassava starch and beeswax reinforced with coconut fiber. From the fabrication of cassava starch and beeswax, now we added to reinforce with coconut fiber. So we weighing of fiber in 10% until 50%, and then we blend with the mixture of cassava starch and beeswax. Then we compact into the mold, and then put the mold inside the hot pressing machine, and we got the sample. Characterization of sample. For thermal analysis, I'm using thermographimetric analysis TGA, and for mechanical analysis, I'm using tensile test and failure testing. And two additional analysis, which is FTIR and SEM, Fourier transform infrared spectroscopy, and scanning electron microscope. Chapter 4, result and discussion. Now I start with the critical slide. We go to result and discussion. First, thermal analysis, TGA, thermographimetric analysis. Okay, from the figure, TGA curve of thermoplastic starch starts to degrade at approximately 250 Celsius. The TGA curve and composite of TPS matrix very similar and superposed but show some variation with the inert TGA. It can be observed that the weight loss percentage of specimen due to product degradation, evaporation. Okay, for the DTG curve of TPCS beeswax reinforced with coconut fiber, it is confirmed wherein the temperature range no inflection point is seen. The fiber addition of the starch matrix have been reported to increase the thermal stability if the fiber and the matrix addition wells, and thus reduce the mass loss in the sample. Result for mechanical analysis. First, tensile properties. The table shows that the summary of the analysis of variance ANOVA. Okay, we can see that if the p-value is less than 0.05, the average tensile strength and modulus vary from one level of polymer mixture to another is statistically important. Okay, based on the figure, tensile strength and this one tensile modulus. So it can be seen that from these two figures, the tensile properties results show that the tensile strength and tensile modulus are higher. Both of the starch composite and coconut fiber increase with increasing fiber content. So, based on the result, the tensile modulus increase rapidly from 10% to 20% of fiber, with an increasing in fiber content and the tensile modulus value. However, tensile modulus at the 40% and 50% of fiber are increment error is remain the same. Hence, there is no significant changes. For failure properties, we can see that in general with tensile testing, the effect of fragile testing meet a similar pattern with the tensile properties. It can be observed that the fragile strength and fragile modulus is increasing gradually from 10% of fiber and to 50% of fiber. The fine-bean might be due to the polymer change has a strong interaction with the fiber, which overcome the weak adhesive of the fiber matrix and increase the fiber content. Now we move to FTIR, Fourier Transform Infrared Spectroscopy. Figures show that the IR spectrum were identical to both TPCS and the composites, provided the main starch composite and coconut fiber is based on the structure of the cellulose. In general, both of TPSC and the composite spectrum show the same band pattern. The width in the range, the strong evidence that the new hydrogen relation are formed between TPCS matrix and cellulose fiber. Axial deformation of OH group attribute the large bonding from 10% to 30% of coconut fiber. The wavelength of OH bonding in the range of 3400 to 3200 wavelength. Next, we move to scanning electron microscope, SEM. There are the defects such as crack, void, and fiber breakage. The figures show that the SEM micrograph of a fracture surface of TPCS B-sweat reinforced with coconut fiber composite. The microstructure of the specimen were different due to the amount of fiber in the sample. This is fabrication result of mold design by using cutter B5 and CNC machining 5 axis. The fabrication of core and cavity of the mold. Chapter 5. Conclusion and recommendation for future research. Conclusion. Objective 1. The successful development of TPCS and B-sweat with coconut fiber composite was achieved using cassava starch, glycerol, and coconut fiber. Objective 2. The thermal characteristic of TPCS B-sweat reinforced with coconut fiber has been evaluated strongly. The test TGA demonstrated a major improvement in the composite thermal stability by incorporation of coconut fiber. And Objective 3. The mechanical properties of TPCS and B-sweat reinforced with coconut fiber has been well determined by using tensile and flexural testing. As a result, a good irregular distribution of coconut fiber within the matrix contribute to a reduced permeability of the water vapor and increasing the mechanical properties of a composite. Recommendation for future research. First, we can make improvement by using composite antimicrobial characteristic to increase the future use of the material. 2. We can study of different type of the fabrication of composite manufacturing method. 3. We can develop the composite coating to further reduce the material hydrophilicity. And 4. We can study the effect of TPSC by using the various type of plasticizer. This product has been made promising for a short-term product such as packaging tray by TPSC improved with coconut fiber. Several surveys has been conducted on potential customers as the real commercialization. So this is the evidence of the picture as a survey. Thank you.